Hi guys, I'm Venkat Sai from IIT College. This is my consulting presentation for my college. I have elected this topic for my consulting presentation in probability and statistics of the distribution functions and expectations. Okay, today's topics: functions of a random variable, expectation of a function of a random variable, variance of exponential distribution, variance of normal distribution. Okay, functions of a random variable. Let y equals to phi of x equals to x square as an example. X could be denote the measurement error in a certain physical experiment, and y would then be the square of the error. Recall method of least squares. Note that fi of y equals to 0 for y less than or equals to less than or equals to 0 for y greater than 0 for fy of y equals to p of y greater than y less than or equals to y, p of x square less than or equals to y, p of minus y greater than root of y greater less than or equals to x less than or equals to root of y, fx of root y minus fx of minus root y. By differentiation, the density of y is fy of y equals to 1 by 2 root pi f of x, fx of minus root y of y greater than or 0. Otherwise, functions of a random variable called. Let x have the standard normal distribution of n 0 comma 1, so that fx of x equals to 1 by root of 2 pi e power minus x square by 2 minus infinity less than or x less than infinity, then fy of y equals to 1 by 2 root y 1 by 2 root pi e power minus y by 2 plus 1 by root 2 pi e power minus y by 2, y greater than 0, y less than or equals to 0, or fy of y equals to 1 by root 2 pi y e power minus y by 2, y greater than 0, y less than or equals to 0. This is a chi-square distribution with y 1 degree of freedom. Let x be uniformly distributed on 0, comma 1. We show that y equals to is minus lambda 1 power minus 1 in 1 minus x has an exponential distribution with parameter lambda greater than 0. Observe that y is a non-negative random variable implying fy of y equals to 0. For y less than or equals to 0, for y greater than 0, we have 5. Fy of y equals to p of y less than or equals to small y equals to p of minus lambda over minus 1 log of 1 minus capital X less than or equals to small y, p of log 1 minus x is 1. Example 1, let x lambda be let x be uniformly distributed on 0, comma 1. We obtain the cumulative distribution function CDF of the random variable y defined by y equals to x power n. Fy of y equals to p of set of y capital Y less than or equals to y, p of set of capital X power n less than or equals to small y, p of capital X less than or equals to y power 1 by n, fx of y 1 by n, y power 1 by n. For instance, the probability density function PDF of y is given by fy of y equals to given 0 less than y equals to less than or equals to 1 otherwise. Okay. Expectation of a function of a random variable. Given a random variable x and it is a probability distribution or its PMF PDF, we are interested in calculating not the expected value of x, but the expected value of some y is a function of x, say g of x, one way. Since g of x is itself a random variable, it must have a probability distribution which should be computable from the knowledge of the distribution of x. Once we have obtained the distribution of g of x, we can then compute g of x by the definition of the expectation. Example 1, suppose x has the following probability mass function: p of 0 equals to p of y equals to 0, 0 pointer. Expectation of function of a random variable column. If x is a discrete random variable with probability mass function p of x, then for any real value function g, e g of x equals to summation of g of x p of x such that p of x greater than 0. B, if the x is a continuous random variable with probability density function p of x, then for any real value function g, e of g of x equals to integral minus infinity to infinity g of x f of x dx. Example 3, applying the proposition for example 1 is e of x square equals to 0 square of 0.1, okay, given values. Applying the proposition for example is e x of x cube or e of x cube equals to integral 0 to 1 x cube dx. Corollary. If a and b are constants, then e of x plus b equals to e of x plus b. The discrete case ex plus b equals to summation ax plus b p of x. Okay, the continuous case, that is discrete case, we can simply observe by using first one we can continuously. First we got both the values are same, the discrete and the continuous case. Okay, moments. The expected value of a random variable x e of x is also referred to as a mean of the first momentum of x. Moment of x, the quantity e of x power n greater than or equals to 1 is called the nth momentum of x. We have zero summation of x power n p of x if x is discrete. E of x power n and minus integral minus infinity to infinity x power n f of x dx. If x is discontinuous, another quantity of interest is the variance of a random variable x denoted by var of x, which is defined by var of x equals to e of x ex of square x. Okay. Variance of random variable. Suppose that x is continuous with density f, let e of x equals to mu, then r of x equals to e of x minus mu whole square, e of x square minus 2u, because a minus b whole square formula. Then minus integral minus infinity to infinity, small converted into small. Okay, last we can obtain that infinite entity var of x equal to e of x square means variance of x needed. Variance of normal random variable. Let x be the normal distributed with parameters in the square find the var of x. Variance of x recalling that e of x equals to, we have that variance of x equals to e of x minus mu whole square equals to 1 by root of 2 pi sigma minus integral minus infinity into x minus mu whole square e power minus x minus mu whole square by 2 square dx. Substituting y equals to x minus u yields variance of x equals to psi square by root 2 pi minus infinity to infinity y square e power minus y square by 2 dy. Relating by parts by using y equals to u equals to 1, dv equals to e power minus 1. That's all. Variance of exponential distribution. From this, we can determine the following: p of x equals to minus integral minus infinity integral 0 to infinity x lambda e power minus x. This is the variance formula. Var of x equals to e of x whole square minus e of x whole square. From this, we can determine the following proof: e of x equals to integral 0 to infinity x lambda e power minus lambda x dx. From this point, we need to use integration by parts to solve this equation. U equals to x lambda, v equals to e power minus lambda x by lambda, du equals to lambda dx, dv equals to minus c minus lambda x dx. Now we can use the integration by parts from the lambda. Integral u dv equals to uv minus v du. Variance of exponential distribution. From the previous, we can observe this type of formulas using the variance of exponential distribution. From this phase, the same formulas are defined as per the exponential contents. Okay. So this is all I restricted in the values. Now remember that e of x equals to minus infinity. That's all about the free space. Okay. variance of same. Now that we have found the e of x equals to 1 by lambda and e of x equal to 2 by lambda, and we can substitute. Okay. Whereafter this is 2 by lambda square minus 1 by lambda square, so 1 by lambda square. It's all about this section. Thank you for watching this. Okay, this is about